I'm back with my coffee. Glasses.
I'm here at Aerospace Bristol, this UK city's landmark aviation museum. It's the home of Concorde Alpha Foxtrot, the last Concorde built and the last to fly. At the upcoming Optica Quantum Industry Summit 2025, we'll dine directly beneath her. If you attended last year, you'll know that the dinner and corridor conversation is what sets us apart. This year, expect a uniquely Bristol backdrop among historic aircraft, but also meaningful conversations with leaders in quantum and photonics. The Optica Quantum Industry Summit will not be shared online. To benefit from frank and open discussions, you need to be at the M-Shed Conference Centre or seated at a table under Concorde. Will you take a seat at the table? This is your last call to influence the future.
Coming up, the Optica online industry meeting on laser cutting and drilling technologies. This 90-minute meeting takes place on Tuesday, November 4th at 10 a.m. Eastern, 3 p.m. in the UK and Ireland, and 4 p.m. Central European Winter Time. This session explores the latest advancements in laser cutting and drilling technologies, two areas transforming industrial manufacturing in aerospace, automotive, electronics and medical devices. Laser cutting uses a focused beam to melt or vaporize material along a precise path, while laser drilling creates micro-scale openings in metals, composites and polymers. Together, they drive efficiency, precision and sustainability across production lines worldwide. We'll have featured speakers from Corning, Precitech and Trumpf. We expect to hear about metal additive manufacturing, making it possible to produce intricate geometries that traditional methods can't achieve. And representing technology enablers, we welcome active Optica corporate members, Raven, Aconier.
So, Aconier is doing laser machines?
And who can forget the demos in Munich from Fluence Technology.
You can knock it, bang it, but the pulses, they are constant, they are stable.
Your attendance is free, thanks to valuable sponsorship from ANSYS. Sign up now for access to the Optica Zoom room to ask questions and network with others during the live meeting. Your moderators are Jose Pozo and Helena Diaz. Let's begin the live discussion.
Hello everyone, welcome. The time has finally arrived. We worked very hard to make sure we had the who is who on laser cutting and drilling in the room. Welcome to the Optica online industry meeting on laser cutting and drilling. And I see very famous friendly faces here. Thank you very much, Christoph from Iradion. Thank you, Celia from Raven. Thank you very much, Ilya from Fluence. Let's have a fantastic 90 minutes. Allow me to remind everyone what do we want to do here. So in the next 90 minutes, what we want to do is to make sure that with the support of ANSYS, we have two teams of companies. On one hand, we have integrators. And as you saw in the opening video, Corning, Precitech, and Trumpf are here in the room to share with us their shopping list and what we can do for them. And on the other hand, we have the 2.1 micrometer lasers from Raven, we have the tools and the systems of Aconier, we have the ultra-fast femtosecond laser from Fluence, we have the company Iradion also offering their technology, the laser technology. The idea here is to make a match, not with those companies only, but also with everyone in the room. Over the next 90 minutes, all of you are panelists. All of you are here to share what you can do for others and what others can do for you. Remember that we do this because we love our corporate members. This is the job that we do for our corporate members. So if you are not a corporate member, optica.org/join corporate, you can find there all the benefits, but the most important benefit is to be your friend. Let me also remind you that we have a great program of online industry events. Today is online laser cutting, but on the 18th of November, we more or less close the quantum year, the year of quantum, with our Optica Quantum Computing Online Industry Meeting featuring IonQ are the recent acquisitions. Write that down, it's really an important date. And we also like to meet our members face to face. And as you saw in the opening video, next week we have one of our flagship events. We all go to Bristol for our Optica Quantum Industry Summit. Very different event than you are used to. They have the quantum companies telling the photonic industry what they need from them to succeed. And on the 19th of January, we have our VIP reception at MoMA that has become an iconic part of the year of photonics. But also remind me that in this event, we give everyone in YouTube to have access to your presentation. That is thank you to the support of ANSYS. So allow me to say hello to the YouTubers of the world. Hello, YouTubers of the world. It is great to have you here over the next 90 minutes. If you have any questions, write them in the chat and I will read them in the room. And that's, of course, also valid for the people here with me in the Zoom room. Over the next 90 minutes, use the chat. Write down what you can do for others, what others can do for you, what your company does, and make sure that we use the next 90 minutes to connect. Allow me to start the meeting today. Today is a very important meeting. Dr. Helena Diaz has worked really hard to have all of you here and finding from you potential customers, suppliers, and partners. The first company is a very important company for Optica. They recently won the Optica i4 prize. We go to Corning, New York to welcome Philippe Leblanc from Corning Incorporated. Philippe, thank you very much for being with us, opening the Optica online industry meeting on laser cutting and drilling the floor. And the attention of everyone goes to, I see you Gorilla Glass Clear, Philippe, goes to you.
Thank you so much. Really appreciate that. Let me present my screen here. Hopefully everybody can see this.
Can you go to presentation mode?
How's that?
It would be better if you press the icon on the bottom right corner. Yeah, that one. I think again.
Even better there.
Yes, now it's perfect. The floor is yours.
Okay, thank you. So my name is Philippe Leblanc. I've been at Corning for 24 years now, and I manage the laser processing technologies capability here at the Sullivan Park, which is the main research center for Corning Incorporated. Just a little bit brief intro to Corning. Corning is located in the beautiful Finger Lakes region of Western New York. The company was actually founded in the same year that Moby Dick was published. We make most of the world's flat glass, or thin glass is used for things like this we're talking right now, and most of the world's optical fiber, which is powering the internet and making all of this possible. So lots of applications around using lasers. We use this every day, and my role is here as the capability leader for laser and laser physics at the company.
Sounds good. My trip to Sao Paulo.
I think we have somebody that's not muted. There we go. Okay, thank you. So let's get right into it. Lasers have become really a fundamental building block of modern industry. They're applied across a very wide range of industries here. You can see I've got automotive to transportation, and that's only because I couldn't find an industry that started with the letter Z. So at least we've got A to T here. Lasers are used to drill and cut virtually any kind of solid material. They're used in cases where you need very high precision. You also need, if you need very low loss of materials or very difficult materials to cut. So they have very powerful advantages. High material utilization, very high precision, like I said. They also have very large process windows, so they're very stable. They're very scalable for filling out, say, a large warehouse full of equipment. So I'm sorry, this picture's a little bit dystopian here with the laser robots, but really, if you've got a large warehouse full of auto, want lasers to be involved. And there are very strong trends in the industry that are favoring the large adoption of lasers, including miniaturization, which is pushing very high precision, automation, which is pushing scalability, low cost, things like the integration of Industry 4.0. We're developing next generation of materials, composite materials. We're using a lot of glass, very Corning here. So we've got thin, brittle materials, things with coatings. And we also have rapid progress in laser technologies themselves. So you've got, the sort of dollar per watt trends is decreasing. So things are much more affordable now. You've got size and the form factor of lasers that are reducing, and you've got new wavelengths, things like burst modes. They're enabling lots of other additional laser technologies. And if you want a little peek in this, there's a plug here for a December 2022 Optica blog post, how lasers are transforming the economics of industrial production. So let me give you a little bit of insight into how to get all this started, what's important. We've got critical inputs here to your laser process around wavelength and pulse energy and the kind of optics that are used. Generally, people use Gaussian or focused optics to create focused spots. There's also more, a little bit other flavors of optics, such as Bessel and non-diffractive optics, flat top optics, vortex beams, and a whole other slew. You can even interfere beams together and create large areas arrays. So you generally have a separation or two different modes. You can have a thermal process, and these are more on the kind of continuous wave optics. This is basically ablating or heating and vaporizing material. And you can see here sort of a ChatGPT that looks like of sort of volatilizing material. It's coarse, but it's very widely applicable. Or you can go the other range and with ultra short pulses, start ripping electrons off of materials and creating very precision plasma plumes. This is a minimal heat affected zone, can be very precise and very powerful. In terms of outputs, you've got lots of quality metrics here about strength, edge strength if you're cutting, straightness, number of, if you're using a brittle material, you've got chips, potentially resistance, you're separating materials. On the drilling side, you've got surface strength, you've got wall roughness. If you're making holes, you're looking at maybe circularity or the concentricity of a top hole and a bottom hole. If you're making vias, maybe you've got incomplete vias. So it's a very wide range of kind of quality metrics. Don't forget, you've got post-process steps. You need to potentially temper the material once it's been cut. You've got chemical etching or coating, certainly several cleaning steps as you remove either debris or accumulate environmental contamination. There's a metrology step very often to make sure that feeds into the quality control. And then you've got sort of a quality QA and a process control where you feed everything back and improve your process. And this is in addition to packing and shipping and all the other processes as well. Make a little plug here for precision machining in glass. You can use, say, Bessel beams or these non-diffractive beams to cut very rapidly through glass in a process that's almost like putting as you would get in like a paper towel. There's a very rapid way, a meter a second or even more, way of cutting very thin brittle materials such as glass. You're looking at damage and etching of vias. You can do this by creating damaged sites, right, in an array, and then use etching to expand those damaged sites into vias. This can be used for, say, the electronics industry. In order to sort of very precisely and with low roughness figure, you cannot beat femtosecond figuring. This can apply very smooth nanometer level roughness if you've got time to do it on materials. And then you can even use more sophisticated processes such as liquid immersion if you want to really mitigate the effects of, mitigate thermal effects and create complex, long, high aspect ratio channels. All right, still some lasers are not magic. So there's still some challenges in laser processing applications. One is process-induced defects. This can include things like residual stress or debris. You've got some process variability. So lasers can be sensitive to roughness or waviness on the surface, contamination, potentially bulk composition, uniformity. The challenge certainly to scale laser-based processes to dense arrays, trying to make very small textures across very large glass, for instance. That can be a challenge in terms of time and cost. Overall cost for the system can be a challenge if you're using things like ultra-fast systems, or you need a lot of them to cover a large area. So capital cost can be a challenge. And then personally, as we look to transfer new processes into manufacturing, there can be a challenge on this technology transfer piece. So that's receivership, which is either the process receivers, equipment receivers. This requires highly trained staff. So that has been an obstacle, can be an obstacle. But overall, a very strong market pull, very strong trends, and advanced technology using lasers. So I think there's a very bright future for laser processing, and I'm excited about the rest of the panel here and the kind of technologies that they're presenting.
Thank you so much. And it's actually, if you can put back your previous slide with challenges, yeah, this is one of the things. It's like what are the major challenges for Corning and what the industry can help you? So what it could be coming from the industry, from the enablers, to help Corning to succeed on these challenges?
Yeah, so certainly, I'm sorry. Was that was a question to me?
Yeah, that's a question to you. That's a
Yeah.
question to Philip. Yes.
Well, certainly, the one because we have a lot of brittle materials, ultra short pulse lasers are a key component of how we do laser processing. So the cost, form factor, and sort of reliability of that technology is a big part of. If I had to pick one thing here that could be influenced by the industry here, would be to keep advancing this ultra short pulse technology. This is short picosecond or even femtosecond. This could go from the lab to kind of, into robust manufacturing. That would certainly be a plus. Lots of things we do here are done at the kind of, as an exhibition or as a concept. And we look to scale and it's just too expensive.
Yeah, actually, yes. Yeah,
Yeah.
so I agree with Jose. I mean, it's like, what is going to be the telescope width? I mean, for you, it's just like, how do you choose it? What is your ideal one?
What is my idea?
Pulse width. Pulse width.
Pulse width. I'm sorry. Yes, pulse width. So we use that spectrum that I have from CW to ultra shorts. We use that entire spectrum for the different kind of materials that we process here, the different kind of materials that we make. But the very finest, right, the hardest things that we do, the very finest level of machining, we use very short pulses. So this is really into the femtosecond, say hundreds of femtoseconds right now in terms of pulse widths. So I think we have pretty good power right now at that wavelength. We just don't have the overall system cost, and sometimes even the sort of form factors. These can be relatively large lasers. And so this is my wish list would be to have a very cheap femtosecond. Of course, just easily done, right? Cheap femtosecond laser.
Yeah. I see. So we have several questions actually, and I would like to call Celia, because Celia, can you open your mic and your camera? And actually, I would like you to make your own questions. So Celia is the CEO from Raven. Raven is ultra-fast lasers, Holmium lasers. Celia? Yeah. Can you make the question yourself, please?
Yeah, first question was, you mentioned in the first slides you presented the emerging technology like new wavelengths, variable repetition rate, and so on. I'm probably very uneducated on glass processing, but for me, all these processes were kind of established, and the next step was the gigahertz processing. Is it something you are thinking about? Is it something you foreseen as a direction for the future? I'm very naive. Huh?
No, I mean, not at all. Like you said, there are a lot of materials, industries, processes that are emerging, right? So it's not like we have very mature markets. We're looking at these trends we're talking about in terms of things like co-packaged optics, right? These things in terms of using glass as interposers, using the next generation of say fiber and cable manufacturing. So as we look to make, implement new materials, new products, we need new processes. So it's all good. And we also find ourselves, I mean, new is better, right? But we also find ourselves sort of revisiting something we couldn't do 10 years ago because we just didn't have things like, burst modes, even in picosecond level, lasers that we can do now. And so some of these things like texturing glass, could be either tactile texture or creating an optical texturing, stuff that we couldn't do before. And now we have new ways of maybe doing this, right? Things like very high rep rates can be used in with galvos or other ways of
Yep.
translating beams across the material. So if you're cutting out a thick sheet of steel to put onto a ship, probably don't have a lot of throughput requirements or things like that. But if you're trying to texture 1 billion square feet of display glass every year, you have to either create an enormous warehouse full of machines, or you have to really crank up the throughput. So so you mentioned gigahertz in particular. Yes, we have done some work around gigahertz, things like, rapid trepanning to make holes. Also looked at combining picosecond and like quasi CW beams to enable high aspect ratio holes in glass. We're talking about drilling. Cutting of glass is a little bit more, as you said, maybe a little bit more well-known and well-practiced. It can still be a challenge if we have very, very thin glass, right? So if you look at the kind of glass for foldable phones, this is something that requires very high edge strength, for instance, break resistance. So as you're making features in very thin glass, you do have to still enable strong edges. You need very high quality of this cut. Not sure if I've actually answered your question or not. So
yeah, you answered
yes,
that. Yes, that you were trying something towards gigahertz, but this doesn't seem like not necessarily the only main direction. There is a lot of things that you are still exploring.
We are working on things. Right.
Yeah, is going to see. So if someone knows about how to do a glass processing, is Fluence. So we have Ilya here. They have a glass cousin called Jasper X0, which is 60 watts with an average powers with 250 femtoseconds pulse. So Ilya, could you please open your and give us your presentation, please?
Yeah, so I want to make sure you see my screen. Yeah, you see my screen, right?
Yes.
Thank you very much for giving me a floor. Yeah, I would say it's a correct address if we want to discuss. Corning is glass, glass is Corning, and Fluence is building tools for cutting and drilling transparent materials, including glass. And Philip from Corning mentioned that drilling is now more interesting and novel topic in glass processing. And I don't have much time. I will try to cover the most important and interesting aspects of glass drilling and cutting using a femtosecond laser, like 250 femtoseconds, which we build at Fluence Technology. So on this slide, we show the drilling capabilities for different type of glass. I'm not showing all type of glass that you can process. It can be Eagle XG, BK7. It can be fused silica. It can be silicon carbide, and our approach. One of the advantages of our approach is to be able to process different type of glass with a high speed, no taper, and with excellent aspect ratio. And of course, eliminating the need of chemical etching as a post-processing step. But at the same time, it doesn't mean that you can't use the etching post-processing step. So this method can also serve as the pre-step to etching if required. Yeah, I will move on to a more established process, as Philip mentioned. So glass processing, glass cutting. So on this slide, we show bezel beam cutting method using the femtosecond laser. So in general, glass cleaving requires the generation of microcracks within the material. However, the standard approach is not suitable for fragile ultra-thin glass, like, for example, with the thickness from 30 microns to 100 microns. So our regime of ultra-thin glass cleaving use ultra-short pulses, like 250, 270 femtoseconds, which does not induce microcracks and resulting in excellent edge quality. So this is very important to reach good surface roughness. For example, the typical surface roughness we reach with our ultra-thin glass processing is 100 microns. And from what I know, the typical one is I'm sorry, yeah, 0.1 micron, and the typical one is 0.5 microns. So also on the bottom of the slide, I'm showing additionally that femtosecond lasers with compressor stretcher configuration can tune the pulse duration from 250 femtoseconds up to 20 picoseconds. And this configuration enables allowing efficient cutting, not only ultra-thin glass, like I'm showing at the top, but also like relatively thick glass, like up to 3 millimeters. And on the slide, we show solder lime 2 millimeters, but even with 200 microjoules and 30 watts of power, you can cut up to 3 millimeters glass in single pass using our approach, and yeah, also up to 8 millimeters with multiple passes if necessary. And everything what I showed was done and can be done with the Jasper X1 laser that we have at our application lab. Everything what I showed during these two slides were done at our application lab, where we gaining experience in micromachining and helping our customers to have the best laser tool for example, glass processing. If we discuss this topic, it's not only glass processing. So our Jasper X1 is all fiber laser. The main idea and feature is to have environmentally stable laser system, which can be mounted in any orientation, which is vibration, has a quite high vibration tolerance, and no cesium, no free space oscillator, which is a very important part of the micro laser system, decreasing the cost of ownership of the laser and the whole micro machine system where this laser can be installed. I think I took more than 2 minutes, and if you have more questions, I'm happy to answer, and please contact me if you want to learn more.
We
Thank
want to learn a lot more because what you're doing, Ilya, is fascinating. But allow me to go back to Philip. Philip, it is great to have Corning with us. We want to understand a bit better the main challenges for increasing throughput. We have many people here in the room that can help you with these challenges. Could you summarize now what is the main challenge that you see of making laser cutting and drilling faster?
Right, so cutting typically is pretty fast if you're making sort of one-dimensional cuts, right? So you're cutting out borders of things, and you're limited then by the sort of acceleration and deceleration properties of either the optics, or if your optics are translating, or the material as you're translating this material. So the throughput can, there are ways of parallelizing cutting. If you're making smaller parts, you can have multiple, split a beam or have multiple beams that are creating parts in parallel. So typically the cutting piece is pretty is okay from a throughput per cost per throughput standpoint. It's all pretty okay. Drilling can be a challenge. So if we look to make, say, in the co-packaged optics standpoint, or from things like glass interposers, things where you have large panels, right, 0.5 meter by 0.5 meter, and you have to deposit, 1 million or so holes into these panels for electronic applications, right? Now you've got a problem of locating the beam, right? Repetition
Philip, I'm
rates are
gonna
usually
help you
pretty
with that,
good.
I think. Philip, I don't think I could help you with that. When it comes to parallelizing, I guess you know the company Megabat Lasers. And I'm here with me, Scott Hamlin. Scott, he's talking about perhaps the needle will increase the amount of needles for laser drilling. You think you can help here?
I'm not so sure. Our laser drilling system, as you know, Jose, is really used for drilling surgical needles. And so these are relatively deep holes, maybe very small holes. But they use pulses on the order of 10 microseconds, not femtosecond pulses. Drilling needles is very different than a lot of other applications. It has to be done very rapidly. We drill 10 needles per second. So as you and I were discussing offline here, what I'm actually interested in is, what possibly femtosecond lasers might be able to offer us as far as being able to drill needles.
Allow me to get back to that later because we will have a couple of more companies. But the guy from Fluence smiled very broadly right now. He's contacting you offline. I know him very well. Scott, hang with me. Philip, allow me to shoot again to see if I can find you somebody who can increase the throughput. Arturo is here from Laserway, and you got some money from the European Commission to actually increase throughput and making laser systems faster. Can you tell us a bit more about what you're doing, Arturo?
Yes, let me share my slide. Can you see it now?
Crystal clear.
Okay, well, thank you, Jose. Thank you, Elena, for the opportunity. Good afternoon, everyone. My name is Arturo Elias Jumbet, and I am the Dissemination, Communication, Exploitation Manager for the project Laserway. What is Laserway? Laserway is a Horizon Europe project whose main objective is to develop extremely high-speed laser processes for sustainable and flexible manufacturing. By doing so, Laserway is innovating in 3 specific fields: photonics and process control, machine design, and programming and optimization. There are 3 technologies within the project with 4 use cases, but for the sake of this meeting, I will only focus on laser blanking and microdrilling. I will briefly introduce the partners involved in each solution. For the Laserway blanking solution, we have Fagor Arrasate in the Basque Country. They are the machine tool builder. Fagor Automation is working on the programming and the control in the process control. We are using innovations from Precitech on the laser head to allow cutting accurately and at extremely high speed. Compotech is providing lightweight composite structures to facilitate the fast movements of the gantry in this machine. Video Systems from Italy, they are providing solutions for in-process quality control, while Module Works in Germany is working on algorithms to make the process to optimize the process and also to make it more sustainable in terms of scraps production using nesting algorithms. RCMT and IDECO are R&D centers. IDECO is the coordinator of the project. They are working, of course, together with the rest of the partners in designing the machine and, of course, optimizing the process. The main use case for this big machine is the production of B-pillars for the automotive industry. I mean, the use case within the project. But the idea is to really provide a solution to this industry in which small to medium-sized batches can make use of the flexibility of laser cutting, which is of course in opposition to the wasteful and more conservative, let's say, press blanking that is used in this industry. In the Laserway microdrilling solution, we have Techniker, also in the Basque Country, leading the developments. They are working together with Cedrak Technologies on innovating in the laser head for an accurate and faster drilling process. Video Systems is also providing quality control solutions here, and Asud and Ernova are end users, and they are of course providing feedback to the developers on the two use cases in this for this solution. The first one is coming from Asud. They are specialized in providing water filter solutions for the agriculture for agriculture. And the idea is with this huge machine, is a very big machine to produce filter cores for these water filters systems. And the second use case is also provided by Ernova. Is a technology previously validated in another EU funded project. And the idea is to manufacture big micro-perforated leading edges for aircraft wings to implement the hybrid laminar flow control technology. This technology allows these micro-perforated panels to decrease the drag forces on the plane, and it has the potential to reduce fuel consumption up to 9%. Well, that's briefly what we are doing in LaserWay related to laser blanking and micro drilling. And of course, if you have any technical specific questions, you can visit our website. You can contact me. Also, I will leave my email in the chat. And of course, we'll be pleased to collaborate with you. And if we need the expertise of any of our partners, we'll be happy to connect you.
Of course, thank you very much for being here. We do have challenges. So let's start the meeting as it should be, with the challenges. Allow me to go to Columbus, Ohio, to give the floor to Ofek Nave from Transmer Corporation, because he has a challenge for all of you. Ofek, thank you. Welcome for the first time at the Optica online industry meetings. Tell us what you do and challenge the people in the room.
Hello, everyone. Good morning and greetings from Columbus. My name is Ofek Nave, and I'm a process engineer at Transmed Corporation, and I have a big challenge that I would like to present to you guys. First, I want to tell you a little bit about Transmed Corporation and what we do. We're really a one-of-one company, and the only in the United States and one of the only in the world that does what we do. And we work, we're a manufacturer, and we work with high purity aluminum and zinc products. And one of our products is aluminum flake, which it's basically a pure aluminum that we get the big saws and we melt it down, and we have this amazing process that we pump this aluminum and then we rapidly solidify it to create this fine flake that's being used for the fuel industry and the automotive industry. And even it's a very good insulation material. And we also, we make zinc shot, and we create different alloys for different purposes. And the challenge that I would like to present you guys with is there is a very critical component to our process that is there's silicon carbide tube. And this is a closed end tube. And this is a tube that we use to pump molten aluminum. And it's gonna be hard to see on the video, but there is 50 micro holes in this tube. And each hole is 0.021 inches with a very tight tolerance. And recently we discovered that a lot of these tubes the holes are either oversized or undersized. And what happens is when we pump the metal through it, if the hole is too big, it's causing us a lot of problems and early shutdowns in production. And if the holes are too small, it's also causing problems. And currently I'm working on a project we have these tubes casted. It's from boronitride silicon carbide. And our problem is finding a company to partner with that's able to drill these holes to spec. And I'm looking to connect with any industry experts. I have a budget for this project and everything, and we're ready to place an order and go into production once we do some sort of trial or confirm that we're able to achieve this tolerance and the holes in spec. And I'm excited to hear what opportunities and ways we could do this and hear from the experts in this room.
The floor is open for questions. Celia.
Yeah, hi Ovek. I'm afraid I cannot do anything for you, but I guess everyone in the audience is wondering, how are you making those holes currently? And
So our company has been around since the 70s, and over our long company history, we've drilled these holes a few different ways. Back in the 70s, 80s, we actually had an operator that was using some special hearing device and a diamond drilling bit, and he would go one by one and drill these holes and listen for any cracking and change the RPMs and the speeds and everything based on what you hear. And it was very long and expensive process and not very efficient, as you can imagine. And this the big challenge is this material is the boron nitride silicon carbide is such a hard material and such small holes that it's very difficult. We've also tried to cast these tubes with the holes, but again, it was either too big or too small and out of our specs, so it was no good for our production. And the most success that we've had was with one, laser drilling, and two, with ultrasonic drilling. But currently, the current vendor who is doing this for us, the lead time and the pricing is way too long and way too expensive. And without this tube, we cannot run our production.
Okay, we're going to find you a solution. The next question is Tadas from Aconier. Tadas, please ask.
Hello, Optic and everybody else as well. So what's the thickness of the wall tube? And if you know that in millimeters, it would be even easier.
Hello, the thickness is a 1/4 inch.
So quite a bit. So it's what we have several millimeters, let's say.
Okay,
Sorry.
next one is coming from Corning. David Dawson Eli, what's in your mind? David wrote the question.
So I
go
had
ahead.
the same question as what's the aspect ratio of the hole? And I think he just answered it.
So it is the thickness is 1/4 inch. So what is the total size of the hole?
The actual size of the hole is 1/2 millimeter or 0.021 inches.
Okay, any more questions for Ofek? I know people are contacting you offline, Ofek. We have 3/4 of an hour to answer this challenge. I want this challenge to be solved on the next 45 minutes. We need to offer Ofek a solution for this because his production right now depends on this. Thank you, Ofek, for being with us. And Helena, please continue this fantastic meeting.
I have one more question for the room, if it's okay.
Of course.
One possible method that I've been researching and potentially would like to conduct a trial, and I would like to see if you, the experts in this room, think it would be a good method. But from my understanding, when you drill such material like a ceramic that's not very good at heat conducting, and the actual laser drilling process would cause the exit hole to be bigger than the entry hole. And we don't want this. We want the hole to be exactly, straight down and not like this or not like this. And one potential method I've explored is doing like a laser guide hole that's smaller than the actual size that we need, and then going with a diamond drill and drilling it up to spec after the laser drilling.
That sounds like a challenge for a very good laser head. So I think later on you're gonna see a presentation from Marcus from Precitech. But before that, I think there is gonna be exactly 45 minutes to answer the challenge. Just to remind, we need a 6.35 millimeter, 1/4 inch deep hole with half 0.05 millimeter radius, and it has to be exactly straight, the hole. We need to find that on silicon carbide. Ilya is smiling from Fluence, Marco is smiling from Precitech. There's a lot of people very happy right now. Also, Trump is smiling. I leave the floor to Helena to continue moderating the event.
Yeah, so thank you so much. And actually, someone that is very, very, very good at giving all the system for all the laser cutting is Precitech. And it's my pleasure to present Marcus Kolke-Hollander. So Marcus, the floor and the attention is all yours.
Thank you, Elena. Thank you, Jose. Good to see you again, and I hope you see my slides already.
Very good.
Excellent. So yes, we are coming from the, let's say, very, very innovative stuff to the boring, old-fashioned cutting. But hopefully after my presentation, you see that it's far from being boring. The work in laser cutting, even in laser cutting of metals, it's getting more and more exciting. And this has many, many topics. And you see my presentation. What if you don't, you not need to take care of your cut quality anymore? So if the machine is doing everything for you. So let's see. Yes, Precitech, as you know it, I just go over that slide quickly. Is still a company. We are worldwide with subsidiaries and with representatives, and we are still 750 people in the world, looking for all the possibilities of applying laser radiation, laser photons in industry. And yes, laser systems, no longer one fits all. This is a presentation actually which was shown by my boss at the acrylic conference last year. And you see that the numbers, the kilowatts actually, which you see at the cutting heads, the numbers are increasing and increasing and increasing. And I myself, I'm with Precitech for 30 years, more or less. And actually, not 12, I would say 12, 13 years ago, there have been discussions on the thermal focus shift in processing optics already at 4, 5, 6 kilowatts laser power. And now we're talking about 200 kilowatts. And we are still talking about transmissive optics. And we are happy that all glass manufacturers have also innovated a lot in the recent years in order to build pure glasses which we can use in our optics. Very, very few absorption in the optics, in the bulk material. And the same with the people who do the coating on the optics. Very, very few absorption in the coatings, coating layers. So this actually, these innovations, these companies, they make us capable to work on those new cutting heads. And yes, we are trying to replace plasma cutting. And just one story, one side story, when Precitech was founded in 1971, actually, there was already a patent existing, which was claimed by the wife of the founder of Precitech. And she claimed a patent for capacitive distance control for cutting tools. And that was for plasma cutting tools. And it was a plasma protected capacitive distance control. And you will see later in my presentation that this is still one of the important stuff. So yes, we are applying photons into processing heads for cutting. And you see the family of laser cutting heads is increasing and increasing all over the years, from small to large, from 2D to 3D, fine cutting. You will a little bit of all see during my presentation. And this is important. If you still want to be a global player in cutting, you need to have that family of cutting heads. So, but if customers see that slides, they just think, what does it mean for you? And let us take care. Let Precitech take care, and let us take you by the hand and show you what is the best for you. So we start with ProCutter Prime today. This is our latest innovation. which is a cutting edge product, which has a lot of features inside, and you will see that features during my presentation. And it's important to have those features these days. So it's not just only photons in, photons out with some capacitive distance control. We have a lot of inside the cutting head. Important is also how we build the cutting head. I'm always a little bit, let's say, careful if I talk about the cutting edge being easily serviceable, because typically we say we don't need any service. But if there is service, you see that there are a lot of cover glasses now inside our cutting heads in order to protect the optics, because any kind of small dust on the optics will directly kill it and will not make the process work anymore. But yes, as I said, there's a lot of inside the cutting heads, which is also based on AI. We have a lot of software in the Cutbox Pro, which is the system which is connected to every cutting head. And one important thing, for example, is that we vary the magnification during the piercing process. You see here from step number 1 to step number 6, how a piercing process in thick section steel, this is a 40mm steel sheet, works, where we start from a magnification from 1.2 to a magnification of 4. And you see that we gradually increase the magnification, which is important to have a very fast and very robust piercing process, because you lose a lot of time if the piercing process it's not fast as possible. So large magnification reduces the fluctuations, and it's reliable. The same, and this is even also important, the same when we start the cutting. We see on the process emissions and on the response of the sensors we have some of the process radiation, and on process radiation we can also react. And for sure we need to work on different magnifications also when the sheet thicknesses increase. So this is also one important factor of those optics, of those moving optics in our cutting heads, that we can easily increase the spot size, the magnification, and react on different sheet thicknesses. And you as a customer in your machine, you can just put in any kind of sheet thickness, and the processing head will align to it and make it work fine with optimized cut curve. Everything is effective and everything is fast. It's already for 24/7 production. This is important, and as I said, it's fully dust tight. This is so much important when we talk about these 80 kilowatts, which we do right now on a standard region process, or 100 kilowatts on the first tryouts. And as I said, we're working on 200 kilowatt processing heads. So it's important that it's dust tight. It's important that we have a very, very accurate gas flow. And it's for sure also important that we have a lot of cooling inside, because still, as I said, still it's not 100% transmission. There will be a little bit of photons always absorbed on optical surfaces, and they will heat up, and we need to take care of that temperature rise just by cooling purposes. Here you see one of the processes where we already apply artificial intelligence. So what we see actually is on the sensors of the inside the processing head, that some of the optics are heating up, which means we have a thermal focus shift, which means if we don't do anything, we will lose the focus. It will not go, will shift from the middle of the sheet to to the top layer of the sheet and the cutting, you will lose cutting. So it's important when we know the temperature of the optics that we react accordingly. And reacting accordingly means we also use the same optics which we use for magnification in order to shift the focus to the right position. And here you see how it's working on the left without BeamTech, which is our tool for software tool in our CutBox Pro, which is measuring all the temperatures of the processing heads and changing the focus position accordingly as we see that there is focus shift. And we know that based on the laser power on time, we know that on the temperature. So there are a lot of sensors working for BeamTech in order to keep the focus point at the right position in order to never lose the cut position, never lose the focus position. And by doing that, we have 80% less burr because we are also keeping the quality of the cut quality in the desired region. So this is BeamTech. BeamTech is actually, I would say, the first Precitech product where we applied AI modules on laser processing. So you see, there's a lot of sensors in a Precitech cutting head, especially in the ProCutter Prime. So we have the PierceTech, which is the intelligent piercing process, the Lasermatic, which is the capacitive distance control. We have BeamTech, which is keeping the focus at the right position. We have the fast auto let's go back. Autofocus. We have temperature sensors. As I said, we need temperature sensors in order to measure and monitor all the heat in the cutting head. Stray light sensors are important also to see if there is starting of a little bit contamination. This you will see in stray light sensors, and then you can also react accordingly. So it's we try to have a full safe cutting process, and whenever there is something going out of process, we can stop and we give alarm signals. So this is what you see here, just on a different scale. A lot of sensors and where they are mounted inside the cutting head. And yes, so with that, with all the sensor technology, with all the closed loop controls, we can also always provide the best cut quality on different materials. Here's just a fraction of materials. So yes, and material thicknesses are getting higher and higher and higher as we want to compete against plasma cutting. And as I said, Lasermatic is, let's say, the first patent which was applied in 1968. 1968, you have to remember, this is a long, long time ago. And Kimla, one of our customers here, it's not only the Lasermatic, it's also the machine which has to work with the sensor, and they do it impressively accurate. So this is just a video which I found on LinkedIn, which is showing how good you can work to when the processing head is working together with a machine builder. Then you don't have to fear that there is any collision during your process. There will be no collision during your process. For sure, this is without laser radiation. I heard some comments during the rehearsal, but this is, I find that very, very impressive. And yes, thanks to Kimla for their excellent partnership over the years. Yes, and for sure, we are also working in the other region, in the micro region, with different wavelengths. So from the short of 355 to the infrared, maybe also one time 2 micrometer. If there is a market for 2 micrometer, this is what we call fine cutter. Typically, as you see, it's something like stent cutting, but there are a lot of more cutting applications also in consumer electronics industry right now with that technology, with that fine cutting head. And yes, as you see, we definitely also work with monitoring devices, online monitoring devices in laser cutting as well. And this is my presentation and I'm open for questions. So if it's about choice, we think we have it all. I think there's nothing missing from the Precitech product range with respect to laser cutting in mediums and ultra thick section guiding materials. And if you have questions, we're guiding you. And we are still innovating, as you see. We are still innovating the cutting world. I think we will be the first ones who will have a 200 kilowatt cutting head on the market. But still, if you want to challenge us, try it. We are happy to work with you. Thank you so much.
Thank you very much. I'm very, very happy to see Precitech like moving forward. Like this is really a big change from the previous years that we were talking, and it's really nice. So now we have Marcus Rutten from MKS. Marcus, could you please open your mic and tell yourself your own question?
Yeah, I hope you can hear me.
Yeah, thank you so much for coming, Marcus. Marcus to Marcus. Or
Yeah,
Marcus
Marcus.
versus Marcus.
And Marcus knows when Marcus asks, there might be a challenge or not. You are 30 years with Precitech, and I think we know each other for 29 of that. Marcus,
Yes.
quickly, when you go to 200 kilowatts, yeah, I mean, I had been involved with 100 kilowatt optics already. What do you think is more important if you go to 200 kilowatts? Is it the coating of the lens, or is it the glass body of the lens? What is more important, or is, yeah, of course, both must be in place, but or what's more challenging at the moment? Let me ask like this.
Okay, we are not coating experts, and for sure we continuously discuss with coating experts on how they improve their technology. If IBS sputtering is still the technology of choice in that case, or is there something else in the pipeline? We don't know. I guess we will lose the one or the other optics during the phase of try and error. Building that head, that will be no question. But from what I have seen right now, as from let's say prototypes of Funktionsmuster, as we say in Germany, functional systems, it's the ceiling is it's even more challenging, and we are going a different way of less screws, a lot of more less interfaces, less possibilities for dust to enter. But what is really important is the cooling gas and cooling water flow. So there are much more cooling water channels in that cutting head as we have now. And for sure, we try to use also the cut gas as a cooling effect, but it's all inside channels, because we cannot expect cut gas to be clean. We cannot expect cutting gas to be that clean as we need it. So we cannot just let it be inside the housing and maybe contaminate the optics. So there's a lot of things we have to take care about. But yes, it's interesting work what people at R&D department at Precitech are doing right now. But yes,
at the same time,
it's a little bit of everything. Yes.
Are you moving from 2-inch to bigger lenses for that?
Yes.
Okay, thanks.
Yeah, thank you so much. And someone that I would like to call Celia, because I mean there is a good proposal that Celia has with the 2.1 micro. Maybe can they help with the new systems that Precitech is preparing? So Celia, can you open your mic and can you show us your Ray-Ban?
Yes, sorry, I was writing a question and
and go for your question too. So yeah, this is it. This is very good.
Philippe, if you can share with me the grade of glass you are talking about, I'm very curious. That being said, here is Raven. Raven is a startup based in Germany. For those who know her, we are speaking of the group of Professor Clara Saraceno. She's developing high power laser and a lot of work around terahertz technology. And we are commercializing part of what is done in the research group, which is the development of 2.1 micron ultra-fast laser based on holmium chalco. It's free space, so we are a bit different than maybe what you can find commercially with thulium, usually fiber-based. What is the advantage? Simply to scale up more easily in energy. So you can see that we can go up to the millijoule level with our laser. We have currently two products. The first one is, I haven't put it here because I don't think it's relevant for laser drilling, but you tell me, an oscillator, Raven S, that is emitting 1 watt at 2.1 micrometer of central wavelength. 100 femtoseconds, 10 nanojoule, 70 megahertz, and Raven L, who can still be tuned, so between 10 to 100 kilohertz, so in between 100 microjoule and 1 millijoule, you make the calculation, 10 watts of average power. And why is 2.1 micron a beautiful wavelength? Simply because of the properties in silicon. So at 2.1 micron, 2 micron in general, you're transparent to silicon. So you can go through, nice, but if you focus down, you actually trigger a nonlinear effect with very little energy per pulse. And you can thus, so by nonlinear effect, sorry, I meant filamentation. And you can thus process directly inside the volume of the silicon. So here I let your fantasy act. You can pre-cut, you can drill, you can do a lot of things. Through silicon vias is the topic that we are really keen to explore at Raven. Spoiler, we are a laser manufacturer, not specialized in laser processing, so I'm happy to collaborate or get insight of any of you in the room. So why we are into through silicon vias? Because we see a lot of applications in different areas. So I mentioned a few here. Maybe the most widely spread is the chip. So an alternative maybe to the dry reactive ion etching, which is currently used for doing through silicon vias. So imagine that we could maybe simplify this process with a new laser. That would be, I think, really cool. Needs to be investigated. Follow us on that because it's still unofficial, but we have a European grant that will start in a few months to investigate this. For MEMS, this is something I've been asked quite a bit as an alternative to ultrasonic drilling to use our 2 micron laser. And finally, for microfluidics, so in polymers, we are actually very absorbed at 2 micron. And thus we can do some very fine processing on the surface. This is in a nutshell, 2 micron and Raven. I hope I've been clear. I think I've been in
very clear, actually. very clear. And this is actually, I mean, this is this is a project that I really like and I really support. And so, Celia, what is your major challenge right now?
I would like to have partners from the material processing side, because building the laser is already a big task, and I think gathering expertise is much more efficient. So if you have applications that you would like to try, and you can bring with this application your knowledge in material processing, then I'm very happy to open my lab, and we can maybe try things together.
Yeah, so there are a lot of people actually in the room that can be contacted for, I mean, can consider about your laser. But now I would like to also to give another perspective for the laser cutting, and I would like to call to Christoph Brundern for irradium laser. This is a totally different approach. So Christoph, could you please open your camera and show us what irradium can do for laser cutting and drilling? You are mute. Cannot hear you.
Thank you very much. Sorry. You can see my screen in presentation mode?
Yes.
Perfect. So thank you very much for having me here in this event. Very interesting discussion. And I think there is some kind of a transition from the last presentation from Celia to now. What I want to show is our laser opportunities for semiconductor and microelectronics processing, because to my opinion, these industries are a paradise for lasers. So my name is Christoph Wunderling. I'm product manager for short pulsed and ultra short pulsed lasers at Iradian. And at Iradian Laser, we are a key supplier for these two industries. And these two industries are very extreme for us because we need to be very innovative in these industries, because these are industries of the extreme. And what I meant with that, I want to show here on the left side by 4 key applications that we address with our pulsed lasers. We already heard of drilling holes in glass wafers. So Ilya presented it, and thanks to you that you already give an insight to that. TGVs is increasingly coming for producing interposers. So what we see here is a glass wafer drilled with thousands of holes. And the challenge here is to be very, very fast, because thousands of holes need to be processed in seconds. This is the requirement of the industry here. The next is PCB depaneling. We see on the top on the right side. So PCB depaneling is an application which is very cost driven. So we need here a cost efficient solution. We also have the cutting and drilling of silicon carbide. So very interesting application. Maybe Ofek, this could also be interesting for you. We are in this business, usually focusing on wafers, so a little bit a lower thickness, but maybe we can here work together and find a solution for your problem. We know the challenges of the brittle material behavior, of the advanced mechanical properties, so it can be a challenge when it comes to quality. And of course, there is another application called silicon wafer dicing or drilling. Celia already mentioned a drilling process in silicon, but also dicing. So the separation of the dice is very challenging. We need to be very precise here, and no contamination of the wafer surface is allowed. So we faced that applications by our different lasers, so nanosecond and femtosecond lasers, which is a very interesting product portfolio. And with these, we see, some different trends. So for semiconductor and microelectronics industry, we need a very high process speed. I mentioned the TGV process. So we have lasers available up to 90 watt, which offers a very productive process. Their process stability is a very, very important point, because if you want to achieve the yields, the production yields in production, so you need a very stable process, you need a very stable laser at the end. And additionally, production quality and precision is a very important point. A very impacting point is here the pulse duration. So we need here flexibility. We already had the question of the appropriate pulse duration for a glass process. So we need a flexibility to offer our customers also the flexibility and choose the pulse duration by themselves. So we have very flexible from 350 femtoseconds up to 100 nanoseconds with our portfolio. And at last, there is the transition to Celia. We need to be very innovative here, and innovation is here a driver for us for developing advanced wavelengths. And Celia already mentioned 2 micrometers, 2.1 with the holmium laser at Ray-Wen. We also have an industry-ready product, thulium-based, a slightly another wavelength, 1950 nanometers, but the same effect in silicon. So there is a market, coming back to the question of Marcus. there is a market for 2 micrometer femtosecond lasers, which is developing very, very fast, to our opinion. We are in partnership here with many companies. And besides that wavelength, there is also another wavelength, which is very interesting, which is 1342 nanometers, another laser, another wavelength, but a similar effect in silicon. So also these wavelengths could be very interesting for, or is very interesting for silicon wafers. So with that, I want to thank you, Helena and Jose, for having me here. And I'm looking forward for your questions and the discussion.
Thank you very much for the amazing support of Iradion and Luxinar, who also, of course, supported our Global Photonics Economic Forum. Christoph, you are fantastic. Allow me to please bring back Ofek Nave from Transmed Corporation. Ofek, you have been reached out already by many of our members. I'm getting lots of WhatsApps giving great feedback for you to be in the meeting. I would like to allow you to take the stage once again, because you are saying in the chat that people can get samples from you.
Thank you so much for bringing me back. I'm trying my best because I can't hear you very well.
Samples.
You say
Samples,
about
yes.
samples.
Yes, we have many samples of either broken or scrap O-tubes. And I have actually some of them right over there. I'm happy to, any company that thinks we're able to drill these holes to our spec, I'm happy to send some of this material for trial. And if we're able to hit this hole size and tolerance, we're ready with the budget and the urgent need to place an order for production. In order we can place an order, we just need to confirm that we can actually hit this hole size, but we're looking to move quick, and I'm happy to connect and explain in more detail, and I have a request for proposal and what we're looking to get and the drawing of the part and any information that's needed. I'm happy to provide and meet and explain in more detail. I'm happy to answer any questions.
Please, whoever wants to receive samples, raise your hand right now. 3, 2, 1.
Wow.
Ofek, you have been the star of this meeting. I am so thankful to you, and I'm really so sure that we can find a potential partnership here. Ofek, thank you so much.
Thank you so much. And
Celia
wrote
has
down
a
some
question
names and emails of vendors and people that reached out to me. And also I will put my email in the chat in case anyone, if I missed anyone, please reach out to me, and I'll be happy to explain in more detail. And I see we have a question from Laserway. So I'll repeat the specs. We're looking to drill 50 holes, that each hole is 0.5 millimeter or 0.021 inches with a very tight tolerance of plus minus 1,000. And the material is boron nitride silicon carbide, which is it's a silicon carbide ceramic, and it has some like boron nitride coating.
Yeah, so we have a question from Celia. So Celia, go quick with
Christoph, okay, 1.5, I get it. 1.9, I get it. 2.1, of course, but 1.3, why?
1.3 it's a very appropriate wavelength for producing nanosecond lasers. So we are not in the regime of femtosecond lasers anymore. And we see there are high investment costs for femtosecond lasers. And we can compensate that at a significant point by producing nanosecond lasers at that wavelength. So we can offer our customers both a femtosecond laser 2 micrometer approximately, and nanosecond lasers at 1342.
Okay, makes sense.
So we have someone here in the room, someone that we really love too much. So Mark Dinning from Genoptics. So Mark, I would like to know what it could be your challenges for this kind of industry. What they can do for you? What is Genoptic needing for? Mark, I cannot hear you. I cannot see you. Mark Dinning from Genoptic.
Yeah. Good morning.
Aha. Can you open your camera? I would like to see you. That would be
was not
nice.
expecting this.
I know.
Surprise.
But you know how it works. So
I do.
okay. So tell us a little bit about Genoptic and what it could be the challenge for the industry here.
Well, Unoptic is an optics and photonics pure play. My specific area is micro-optics for use in data centers and semicon, and also high-end optics for quantum. And you're asking what can the industry do for, or what do we need from the industry?
Yes. So what is the challenge? How you can challenge these people?
Well, I mean, it's just in understanding the applications. So as many of the speakers have already gone into detail today, but you know, where specifically can optics and photonics provide an advantage? So via hole drilling, annealing. I know we're already in those areas, but where can we further our access to those markets?
Yeah. Is it something right now that really catch your attention until now?
Say that again.
Is it something that really catch your attention until now in this meeting in particular?
No, just as I mentioned, just how advantageous photonics can be in these arenas. It's something that I'd say no other technology can do. I mean, I come from the semicon industry, and for instance, patterning transistors onto wafers, it's only can be done with photonics. Perhaps there are other arenas where we can provide solutions that take advantage of all the characteristics of photonics and optics.
Yeah, well, I can see a lot of the collaboration that could happen here. But now we are going to move to one of the biggest laser cutting, laser drilling, laser transformation systems in the world. And this is Stefan Roblin from Trump. Stefan, the floor and the attention is all yours.
Thank you very much. I hope you can hear me and you can see my screen. So it was already necessary to put on the lights because it's getting dark outside and time is moving forward. So I want to introduce Trump shortly and myself and go into some application details. So Trump is family owned. It's a technology leader, as you introduced it. Thank you much, Helena. We're customer focused, so we have over 70 subsidiaries all over the world, so close to the customers. And we're innovation driven, so there are many funded projects, scientific areas where we work on photonics. And also it's a sustainable company because our owning family is really valuing that high. So to give a quick introduction for myself, I'm the product manager for ultra short pulse lasers. So all Trump femtosecond lasers are under my portfolio. And of course, there were already many discussions. So I think Optic, the last slide is for you. I can tell you that. So yeah, Trump has a wide portfolio of different laser technologies and different machines also, so also machine tools. And we're going from big dimensions. So we have seen already 40 millimeter thick sheet metal, but also for high precision. We are able to go into the femtosecond regime in microprocessing, thin copper films in this case for electronics or also semiconductor industry with femtosecond lasers. And then in combination also with the right optics, we deliver the laser sources to it. And we have also global application centers where we can do the testings. So there's one in Santa Clara, there's one in Germany, of course, in our headquarter, and also China, Korea, where we're represented with our own application labs. We also heard already about laser blanking, so large dimensions, not micrometers, but meters. We have like coil editions for our true laser 2D cutting laser system. So that is a machine tool business unit, but it also helps raising the productivity and reducing waste in large scale productions, for example, automotive. Then we already have heard about silicon drilling, silicon processing for semiconductor industry. So that is also where we are present with our laser sources. We are present with our application experience, and we can also support and go into details to adjust and find the right laser parameters. And then the metal drilling, we have heard that for laser cutting or laser drilling, it's not like we know the mechanical drilling, but it's positioning of the energy in a really small focus. So there are also different optics, different scanner systems. Also beam shaping helps to improve laser drillings. And then this goes into membranes, filter, large area applications, into water filters, for example. So there are many industries and application ideas or possibilities where you can use the laser. Looking more into the industries, for example, inside a car, there are many laser applications. I just want to highlight two of them. So one is the brake disc. I hope I can choose this one here. The brake disc, where we use the high-speed LMD. So that's not cutting or drilling, but still it's a laser process to coat for environmental improvements. But more of a laser processes in battery module manufacturing, like cleaning, contacting, welding. So there are many applications where you could go into. And as you can see, there are many more around the cars. But also in other industries like the consumer electronics, smartphone is really present in all our hands. So we also go from like cover glass cutting or modification and etching. Actually, we have the laser sources and the optics to it to have really challenging processes to increase the damage threshold there, or the OLED cutting, like the film cutting with the UV femtosecond laser, for example. So then I'm looking towards OPEC. This is not the slide I was mentioning before, but here we have the tube drilling as an application example of the medical industry. Also, marking lasers are a part of the TRUMPF portfolio. For black marking, for example, this can not only be used in medical, but as an example here, tube cutting is possible. We have seen stents being cut in the video before. So that is also possible with the TRUMPF laser, with solid state optics, or with a scanner also. And the welding is also a possibility. So for each industry, there are different materials. We have heard a lot about glass. So also from my portfolio, I'm happy to present some of the application examples here. So the top side, as we have discussed today a lot about glass, we have the ultra-thin glass separation with high requirements on the edge quality. So that is possible with TRUMPF top cleave optic in combination with a true micro laser. The shaped edge, so where we do not only generate a straight bezel beam, but we are able to shape this edge to put on a chamfer to also increase the damage stability. And through glass vias, in many contexts we have heard about it. So that is also an application where we work on. And I also mentioned in the comments section that depending on the thickness of the glass, of the aspect ratio, of the roundness requirements, there are different laser parameters. And that is an advantage of the ultra-fast lasers, to adapt pulse duration, pulse energy, burst modes. We have heard questions about gigahertz burst. So there are different possibilities, and not only the laser modification needs to be adapted, but also like material, the laser process, but then also the following processes like etching, the coating, and so on. So there are many more processes, and in the end, we want to have a good final end product, and the laser is one part of it, and it just needs to match into this whole puzzle. Then there's like the PCB standards, so to say, processes up to now with ablation, separation. Also, PCB marking would be possible. The micro cutting for temperature resistant materials like Invar, or temperature sensitive materials like copper, as I've shown the small bicycle on the finger, and large nanosecond applications, large area cleaning processes, as I said, for battery modules, or here for tire molds, and the ultra fast drilling. So that is the quick wrap up. And behind that is a large portfolio of different products, as I mentioned, from marking lasers over CW. We've heard from Corning that we have the whole range from CW to ultra short pulsed, depending on the material in glass, but also in sheet metal, of course. We have optics and sensorics to it, matching to the laser sources. So that's also really important. And in the center here, the ultra short pulsed laser portfolio up to 1 kilowatt by now. So also inside the ultra fast lasers, a really wide range of different laser sources and parameters available. And then if we look on the bottom right, or the right side, with secondary sources and EUV, this is the future applications. EUV lithography is already up to like state of the art, but secondary sources to go into photon acceleration, electron acceleration, or neutron acceleration for different scientific applications. So that is the innovation part where we're moving on, and to bring that knowledge then into industrial products. That's our approach. And now for OFEC, the challenge is accepted. So there was beforehand, but the challenge is accepted for different technologies. Feel free to contact me or us if you have application ideas to go into. So I'm happy to support.
Stephen, thank you very much for bringing Trump all the way from beautiful Ditzingen to this meeting. We have a couple of questions from you. The first one is coming from one company very close to you. We go to Jena. We'll go back to Mark Dining from Genoptic. Mark, what's on your mind?
Yeah, thank you for the nice presentation. I was curious what the role of galvos and scan heads is in your solution, because you're going to have to aim the photons in some manner. How do you do that?
Yes, well, we're the laser manufacturer, so we produce the source, but in our application labs, of course, we have different scanners, different galvos to support and to bring the energy, the photons onto the workpiece and to improve. So we support in this case, and then our customers are free to choose which galvo scanner they use, or which other possibility, whether it's a solid state optic like our top leaf optic we offer, or a polygon scanner for large area applications. It's open, but it's of course, as I said, in the process from laser manufacturing or laser modification to etching in the glass process, also here the whole solution plays a role. So the scanner needs to have the right interface to the laser, that they can communicate, and that we position the pulses in the right spot at the right time. But we're open.
Thank you, Stephen. The second question for you comes all the way from Iridium Laser. Christoph, tell us what's on your mind.
Hi, Steffen. Thanks for the good overview. Great overview.
Thank you.
I was wondering about the silicon drilling. What is the wavelength that you use there, and how have you avoided the contamination of the surface?
Yeah, there are different options. So we offer laser sources from infrared over green UV, and also deep UV. And it depends on the different part and the different geometry. We usually also use infrared in this case.
Okay.
Yeah. And there also, if you adapt the process parameters, you're able to have like we have it in marking, where you have like a cleaning process, then a marking process, and then a contour process. So you can have multiple steps of processing also in this drilling. So you have the possibility to also remove afterwards if you would have some debris.
Yeah. Thank you very much.
Mm-hmm.
The next question comes from Gareth Pierce. Gareth, please unmute your phone, your microphone, and tell us what's on your mind. We can see Gareth, but we cannot hear him.
Gareth, you may be on mute.
Allow me to read the question from Gareth. How suitable is top clip for processing transparent polymers?
Yeah, so actually we had a nice sketch inside the Corning presentation of Philip to see how a Bessel beam is generated. So the intensity distribution is like vertically through the material. So as long as the material doesn't pick up the energy before it hits the intersection point, so to say, it would also be possible to use in other transparent materials. But this is actually a challenge we should accept and test in the lab.
So I am very happy to make sure that the Strathclyde University sends you some samples for that. Gareth, thank you very much for joining. In a meeting like this, we save the best for the last. So allow me to say this: you all have been great, but now we go to Lithuania to showcase the workstations that will integrate every single laser presented so far. Tadas, thank you very much for being with us. Acho, the floor and the attention of everyone is yours.
Hello once again, everyone. I hope you hear me well.
Loud and clear.
Let me just share my slide. So you should be seeing my slide. And it's very fitting for me now to be at the end because of the presentation I prepared. Because, well, we do laser machines. So I'm a laser guy. And let me start with a little bit of heresy in that. So nobody needs your lasers. Unfortunately, nobody needs our laser machines either, because what we saw from OFEC as well, people need holes, cuts, etc. So we need to provide real solutions for that. And if we talk about electronics and chip packaging, well, nobody needs holes either. So when we are talking about TGVs, etc., it's only part of the solution. And what people really need is a final interconnect, so a metal connection, conductive connection between multiple layers. And that's in situation like this where one of our technologies comes in, where we are doing both things at kind of the same time with the help of laser. So we are drilling the vias, be it glass or some other material. And we also have a special laser plus chemical process where we can plate copper traces and copper into the vias to do something like that. So so yeah, just a reminder from us to always look at the whole process and take all process into account, because when you focus on the very small area, those local efficiencies doesn't really matter that much.
You're mute. Yeah.
All right, Tadas, thank you very much for this. Tell us, what kind of company that you have seen so far today, you're going to have an interesting follow-up after this?
So I don't know if we would take the silicon carbide drilling challenge ourselves, but I have some ideas to suggest where to check it out. So probably I'll make a list of that. Also, 2-micron lasers and silicon is an interesting thing. Maybe we can achieve in silicon a very similar thing that we are achieving in glass. So not only to form via, but to also enable plating directly after the via of silicon to have that interconnect instead of just via. So I'm quite confident that something like that could be achieved with 2 microns as well.
Adas, you have to agree with me. This was a great use of the last 99 minutes of your life. I think the success is in the follow-up. I'm about to close the meeting for the YouTubers in the world. For those of you who want to have a drink, a virtual drink after the meeting, you can stay. But allow me to now close the event for those online YouTubers who have followed the live stream. All right. Thank you very much, everyone, for joining this great meeting. My team, IT team, please cut the live stream. This becomes now a private meeting with my friends having a virtual drink. For those of you